Hello and welcome to our group presentation. Today we'll be providing a review of the article MapReduce, Simplified Data Processing on Large Clusters by Jeffrey Dean and Sanjay Ghemawat. This article review was produced by Daniel Blundell, Dao Tao Pan and Yi Wang. In this review, we will firstly identify the motivation for the work in the article. We will then explore the specific algorithm Dean and Ghemawat use in its implementation. Then we will go on to describe the basic concept of MapReduce with examples. We will also discuss a few other applications for a better understanding. We will discuss how MapReduce handles fault tolerance. We'll have a quick look at the pros and cons of MapReduce. And then finally, we'll outline a summary of the main points at the end. So what is the aim of the article's work? MapReduce is a programming model and an associated implementation for processing and generating large datasets. This allows programmers without any experience with parallel and distributed systems to easily utilize the resources of a large distributed system. Dean and Ghemawat's implementation of MapReduce runs on a large cluster of commodity machines and is highly scalable. MapReduce is capable of handling the processing of data on the order of terabytes, distributed across thousands of machines. So what exactly is MapReduce? Well, MapReduce is a parallel processing technique for processing data which is distributed on a commodity cluster. Okay, but what is a commodity cluster? Commodity cluster computing involves the use of large numbers of already available computing components for parallel computing. So, MapReduce is a parallel processing technique for processing data rather than processing the data serially, saving a great deal of time. MapReduce allows scalability across hundreds or thousands of servers in a cluster at one time. Now, let's look into the real meat of what MapReduce does. The algorithm structure is simple with two stages called map and reduce. Hence the portmanteau MapReduce. Map happens first, and the input to the map stage is the input of the entire problem, and the output of the reduce stage is the output of the entire problem. The data is transmitted in the intermediate format from the end of the map stage to the beginning of the reduce stage. The data here is all stored in key value pairs, and so all the data in both stages is accessed using its key. A unique key that we assign from in the intermediate format, and a unique key that we assign in the input format. Likewise, in the reduce stage, we use an iterator to access values from the intermediate format, and this allows us to have intermediate data that's much larger than we can fit into memory on the machine running the reduced stage. The code snippet on the right is from the article, and this is a simple word count application. In the map stage, we assign a key, which is a document name, and a value, which is the contents of the document. The algorithm iterates through the words in that document, and here for simplicity, it assumes that each word occurs once for the count, and we assign the value of 1 to the key, which is the word for our intermediate format. Then from the reduce stage, the key in this stage is the word that we assign in the map stage. So each reduce will be in charge of counting the occurrences of a specific word, and so iterates through the counts in each document of the occurrences of a particular word. and omit the result of the total number of counts in the bottom documents for this particular word. Since MapReduce is so general and only requires the data to be structured in key value formats, this allows a wide variety of applications. Let's look at the specific execution of MapReduce. This is a diagram from the article showing the MapReduce programming model architecture. Looking at the master node, this is responsible for the load balancing and assigning tasks to a particular worker node. It's responsible for assigning map tasks to map workers and likewise the reduce tasks to reduce workers, as well as monitoring the progress of each of these tasks. It also optimizes for efficiency. The process starts with input files on the left, and these are split according to their keys, and this set of keys is sent to its corresponding map worker. That map worker will do whatever computation it needs to and store the output of the map task, which is the intermediate files locally at its machine. Once it's done that, the worker will contact the master node, and that master node will assign a worker to the corresponding reduce task, and once that reduce task has completed it will output its final data, the final data for the entire MapReduce. It helps to make things clearer with examples. Let's look back at the word count algorithm from the article. Suppose we have a list of documents and we would like to count the frequency for each unique word. To make it simple, assume we are only using one machine to do the calculation. One master process could fork many processes or threads. Each thread gets one document to do the splitting and mapping work. After this finish phase, every thread sends its work to a central queue to group the same key together, called shuffling. Then, this does the aggregation work for all the same keys, or that is to say, it just adds all values of the same keys together. Suppose we are using a distributed system to solve this problem. Like the example above, the main process will be the master machine and each thread will be the worker machine. The processes are similar, except in a distributed system it involves the asset property of distributed systems. Moving away from the word index example, there are other applications for MapReduce such as distributed grep and distributed sort. Grep is a Linux command for finding a key word in text. Suppose we have millions of documents that have to be searched for a list of keywords and we would like to know the lines that contain these keywords. First of all, we split millions of documents to different machines and each machine gets the keyword list. Each machine can run its grep program to get keyword and relevant line pairs. Then we shuffle the same keyword together, finally combining all lines for each keyword. This is the reduce phase. In the case of distributed sort, suppose we get a huge list of key record pairs to be sorted. Firstly, we split these records to different machines. Each machine sorts the sublist according to the criteria, either by key or by value. In the shuffle stage, we put the same key or value together. The reduce stage in this example is not as important as with grep and word indexing, since the reduce part just combines all the intermediate results together. There is no aggregation operation. An important procedure in maintaining functionality in such a system at scale is fault tolerance. The master node will ping worker nodes periodically. If there is no response in a certain time, the master node will mark the work node as failed. If this happened in the map phase, the task will be rescheduled by the master node, since at this phase, the result is stored in the local file system. However, if the failure happened after the completed reduce task, there is no need to reschedule the work, since the output has already been sent to the global file system. As there is only one master node, we assume and hope the failure of the master node is unlikely to happen. A way to reduce the chance of this is to perhaps ensure the hardware is the best quality and resilient. But suppose the master did fail. With the master node, a new copy will be started from the last checkpoint. Because the map and reduce functions are provided from the user in order to maintain fault tolerance, the user-provided functions must be deterministic or atomic commits. In the map stage, whenever there is a completed task, the worker node will send a completion message to the master node. If the master node gets the completion message from a completed task, the master node will ignore the new one. If this occurs in the reduced phase, an atomic rename operation provided from the global file system will guarantee that each finished reduced task will have a distinguished name. Before we finish, we will outline the main pros and cons of MapReduce. Some of the advantages are MapReduce is designed for a distributed system to handle a huge volume of data. Thus, parallel computation is its nature. Because MapReduce is designed for a distributed system, it is easy to scale. Tasks are split into small parts so that the memory requirements become lower overall. The main functions are map and reduce, and this feature makes it a relatively simple model. Some of the disadvantages are MapReduce has a high latency, so it's not good for using in real-time processing applications. The tasks must be able to be defined in terms of key value pairs only. Intermediate processes cannot talk to each other. If in the map stage there are too many distinguished keys, sorting will take a long time to finish, thus decrease the performance. Well, that about does it for our article review. In a nutshell, MapReduce is a programming model geared towards parallelization. The MapReduce implementation is based around drawing upon the resources of hundreds or thousands of ordinary machines working in parallel to compute large-scale tasks of sorting and searching. The input data to be processed is in the form of key value pairs. The general implementation is predicated on having a master node which is responsible for the load balancing and assigning tasks to particular worker nodes. MapReduce is easy to use and has a wide variety of cloud-based distributed applications. MapReduce is also highly scalable.